until I realized those uranium things have been exposed, so they have a covering of aluminum oxide. That's what makes it not attacked by either the fluorine or the UF6. So what is something that's very well aluminum itself will automatically develop this called I don't think that's any major secret for anybody. Okay, now you've got this, plus everything else that became volatile by fluoride addition. Okay, there are other things that behave like this. So you got to separate out the uranium because that's the useful part, and you just pass it through a powder of sodium fluoride, beryllium fluoride in the detective mixture. That will absorb it out. This is known. Okay? People actually in the industry use sodium fluoride, magnesium fluoride, but magnesium is in the same family as beryllium. I think this should work. Then you get the UF6 here. How do you turn it into UF4 so that it becomes a fuel salt? You add hydrogen to it. Okay? This is an exothermic reaction. It will react with the two excess fluorines, so you get sodium fluoride, beryllium fluoride, UF4. That's your fuel salt. Plus 2HF. What do you do with the HF? You can do electrolysis of it. Okay? Do electrolysis. This is a liquid. You will get F2 and F2. So you get this is what you need. This is what you need here. No waste. That's our model. Never have any waste. Okay? So this won somebody a Nobel Prize. Last one. I don't know if that's pronounced correctly. Why should you get a Nobel Prize for electrolysis? Because at that time, no one could produce fluorine as an element. Nobody could produce fluorine as a chemical element by chemical process because it's the most electromagnetic of all compounds. Nobody could produce it. This guy did it. You can't directly electrolyze this thing even when it's a liquid. Stays a liquid even at minus 50 C. But if you add a salt to it, which is potassium bifluoride, that can provide the ions that you need to do electrolysis. So this one is earlier. So now you've got stuff that's not volatile mixed with this. There's only volatile stuff. How do you do that? You vacuum this. Since it's not volatile, if I just pump on the vapor, you don't ever have to touch anything. Just let it pump on the vapor. Most volatile stuff will come out. At that point, it's a white solvent leaving behind the non-volatile oxides. So you can imagine doing this. Very simple. Much simpler than one fluid reactors. And most of what's written by Oak Ridge by just doing these simple stuff. This is what the industry already uses, so we know it can be done. We don't know how to do it. No, fluorine is not something you would like Fantai and his RAs to touch, but you know, professionals know how to do this. Now, how do you get a nuclear battery? There's an effect called the Seebeck effect, where you can transform heat difference across a bar to a voltage drop. And this is how thermocouples are made. There's a Seebeck coefficient times the temperature difference between this end and this end. If I know this end, I can measure the temperature. That's what we use to measure what the height is in molten salt reactor. But if you have a voltage drop, you should be able to drive the current. And that's just the concept of the battery. So you put a semiconductor, you dope one to be N-type, you dope another to be P-type. That leads to a battery. If I have a hot end on this side, and a cold terminal on this side, and I have an external circuit involving a pump, I can drive this pump just by this heat difference. So how much can you get? What's the efficiency? It's not great. Not as good even as solar panels, but it's pretty good. Lead perlite has been shown to be about 10%. Silicon germanium is about 0.2%. Graphene in the laboratory has been reported at 50%. So that's enough to drive 8 pumps, and you only need 2 of them, okay, to keep things as a first line of defense, okay. So if Fukushima had these batteries there wouldn't have been no accident. It's only because they had to go to chemical batteries. The first line of defense is to ensure we never have a repeat of Fukushima. The second line of defense is if you have bad things in your computer, what do? You do core dump. You have bad things in your nuclear reactor, what do? You do a core dump. Suppose something happens and you absolutely have real problems up there. What do? You want to move the salt to someplace where you have cooling prepared. All right. So here's an example where I have 340 megawatt molten salt, and I think I'm in trouble. So you dump it. You don't have to make a decision. For example, you have a loss of coolant accents. You're not able to keep the fuel salt cool, so it gets hot. But under your pump tank, you have a freeze plug. Okay, it's been refrigerated. So when the electricity goes out, it's no longer refrigerated. The decay heat in that melts the salt and it goes out. We have lots of freeze plugs in our rack, but we don't have any radioactivity. So we find it hard to unfreeze things. But this will automatically happen. Okay? The decay heat lets the flow into drain by gravity, no pumps, into 4 uninsulated dump tanks. What are those dump tanks? Build them out of spheres. What do they contain? They all contain buffer salt, because you wanted this highly radioactive stuff to be diluted and made into a more dilute solution. And you make them spheres, not because you want small radiating area, but because you want to be strong. When you build equipment, the weakest points are always where you have sharp corners. That's where the stress is piled up. So what's the thing that has no sharp corners? It's a sphere. They built in a sphere, you drop it down, you've engineered it to bring, it's bigger than my hand, but not much bigger. And it freezes, because it's diluted in all the salt. But nuclear will always win out over chemical. So you just wait for enough, it will eventually start to melt it. But the decay heat is all the time dropping. So if you've stalled things for about an hour, that's critical. Then it melts it, and it reaches completely molten. Then it starts increasing in temperature. But the black body radiation from the metal surface is increasing as T to the 4th. So when the temperature increases, black body, that's what we astronomers love, right? You can count on black body radiation. You may not be able to count on convection, you may not be able to count on many other things, but black body radiation, yes, it will work, okay? So, you've engineered so the temperature never gets above about 500 Celsius. Why 500 Celsius? Because if you get above 500 Celsius, the concrete will weaken. Get much above it, it will fall down and collapse. That's why 9/11, the buildings collapsed. It wasn't that they melted it, just weakened the rebar enough. So you want to make sure you never reach 500 C. That's not enough to destroy concrete. So as you radiate more, the decay heat is dying all the time. So after about a day, it will start to freeze again. And then after a day, it will freeze, it will get colder and colder. And after, let's say, a week, the emergency is over. Now you've got this stuff in the tank. We better clean it. How do you do it? Easy enough. Cover it up. Don't let the radiation out. The decay heat, after another week, will melt it again. It will drain out. Now you treat it. Okay? So it's impossible from the second line of defense to have a Chernobyl. The third line of defense is something that Ron Tam worked on. What's the worst nightmare you can think that can happen to a nuclear power plant? It's taken over by some guys who are crazy, and they shoot the rocket at your dump tank, L4. Now, this dump tank is 4 inches thick, 10 centimeters thick. So it's like armor plating of the heaviest tanks in World War II. So it's not so easy to knock a tank out, especially if it has no sharp edges. Okay, they were typically bombed, but you have really good aim. Bang, right head on. Okay, now it's split. What do you do? Well, here's where the contents will spill out on a steel plate below the tank, which radiates black body radiation through the salt. It's transparent above it. You heat up the plate, it will radiate right above it. This area is by definition much larger than in the sphere, because for the same volume, the sphere has the least area. So whatever you spill it out will have a larger radiating area, and therefore it will be able to get rid of the decay heat before the salt is vaporized. It takes, it to become an M star, and that, well before that happens, you'll get rid of it. So it gets into the dome. The domes that are built today are safe. They're built to withstand airplane crashes while letting out the decay heat, but no radioactivity. So sooner or later, the salt will freeze, becoming immobile, optimally in less than 10 seconds. Okay? So there's no way, you may have destroyed the plant. Okay? No way it's going to get out in the environment. But there are always anti-nuclear people who will think of something. So I'll think of a first for them. What if somebody drops an atomic bomb? Yes, you will release radioactive fallout all over the place. But I could drop that same atomic bomb on a field of solar panels, and you will get radioactive fallout everywhere. So that's not a reasonable argument, okay? Okay, I think I will stop here. Thank you very much. This video is going to be posted on YouTube, so I didn't want the YouTube audience, just be left hanging in the air. There's a second reason why I wanted to finish this talk, and that is these take-home messages I wanted to give to the astronomers. In particular, I want to ask for your help, and I'll state what the nature of that help is, okay? So let's begin with these take-home messages. This is kind of a summary of what the talk was about. First, you have to satisfy these four conditions: that it's sustainable, that it's safe, it's secure, and it's superior in cost. Sustainable means that you can use resources in a way such that future generations have access either to the same resources or to better resources. The better resources, hopefully, is fusion, okay, which is almost inexhaustible, the amount of deuterium that's in the oceans. And when I say inexhaustible, I mean, for the age of the Earth and the Sun. So thorium, just the proven thorium reserves, high quality ore or stuff that's already set aside from rare earth mining, is in fact enough to supply 100% of the world energy needs for 400 years roughly. So the reason that current nuclear is not sustainable is because it only uses 1% of uranium. Roughly speaking, thorium is more abundant than uranium, but the proven reserves are coincidentally about the same. So if you only use 1% of the energy and you throw away 99%, and you were to try to use it for all the energy needs, it only lasts 4 years, okay? That's clearly not sustainable. 400 years, you hope that's enough to develop fusion, okay? So there's no waste except the fission products that decay to background levels in 300 years. It's safe. By that, we mean it requires no operator intervention. Anything that involves human decisions, to err is human. So you will always have mistakes. So you want a reactor that doesn't require human intervention, like the sun. Okay, it just runs. You can count on the sun tomorrow to be like it was today. Okay, so except for advanced scram. By that we mean, something's on the way. There's going to be a huge typhoon or, a tsunami. So you want to shut down the reactor in advance. That's the only thing that requires human decisions, where you have enough time to make decisions. Otherwise, everything else operates according to physical principles. It's secure. You can't make weapons out of it. And we explained that because you always had U-235 2 that's mixed with the U-233 in a properly designed 2-fluid molten salt breeder reactor. Now, there's a downside to relying only on that because, as I said last time, that requires a spectrum both to have hard neutrons as well as soft neutrons. So you get spectra, SEDs, that are epithermal rather than thermal. So if you want a more thermal spectrum, if you want a quicker time scale to get up to a full fleet, you would like to have a softer spectrum, which means that you lose somewhat in security. And the way to around that is an optional thing, which is just to add a little bit of plutonium-239 with the thing. Plutonium-239, when it captures a neutron, will always produce plutonium-240. And that's a current weapons deterrent, because this thing is so large, it can spontaneously fission, right? It's just not immediately going in, come on, but you let it in, absorb it, and there's a finite probability it will tunnel